In today's lesson, we're going to be looking at the remainder theorem. So in a previous lesson, I'll link that in the top right-hand corner, we had talked about the idea of the division algorithm, and we discovered that any polynomial, so in this case here, let's say p at x, that'll break up into its quotient times divisor plus its remainder. So in this example here, what we have is we have any polynomial, p at x, if it's divided by, in this case here, x minus a, then the remainder is said to be the polynomial evaluated at a. To see why this is true, notice here we have our division algorithm, which I've written down here. And now we want to show that, okay, if my polynomial is divided by x minus a, that's going to give me a remainder of just the polynomial evaluated at a. So we have the following generalized long division statement. What we want to do is apply this when my divisor is x minus a. So let's go ahead and change that. In which case this will be my polynomial at x is q at x. It's not your divisor anymore. We know what the divisor is. The divisor is x minus a plus your remainder here. Now we're claiming that the remainder is just the polynomial at a. Well, what does the polynomial at a look like? Well, the polynomial at a would be p at a is q at a minus a plus the remainder evaluated at a. You'll notice here right away, this cancels, and what are we left with? We end up getting that the polynomial at a is exactly equal to your remainder at a. It's worth mentioning here that the degree of your divisor is 1, so therefore the degree of your remainder must be a constant term, in which case we could just write this as a variable k, and that could be, any real number here would be your remainder. So therefore, given a polynomial p at x, if divided by x minus a, so it has a linear divisor, then you know the remainder is the polynomial evaluated at a. There's a direct result that is very useful with this here, and it is that if the polynomial at a is 0, then x minus a is a factor. And to see that, you can see here that in this situation here, if you have a polynomial p at x, and you go ahead and divide that by x minus a, you'll see here if the polynomial at a is 0, that essentially means that your remainder in this case is going to be 0. And if that's the case here, that means that your polynomial p at x decomposes into its quotient times x minus a. So in this case here, you can see fairly easily that x minus a is a factor of our polynomial p at x. All right, let's take a look at some applications of the remainder theorem. In the following example here, we want to find the values of a and b such that you have this polynomial, degree 3 polynomial, such that when it's divided by x minus 3, it has a remainder of 52, and when divided by x plus 2, has a remainder of negative 18. So this is a direct application to our remainder theorem. First, we'll define p at x, and we'll let p at x be our polynomial x cubed plus ax squared plus 5x plus b. And as we said here, your p at a is the remainder when divided by x minus a. So therefore, the one piece of information that we have is the polynomial evaluated at 3 must equal 52. And the reason for that is when I divide this polynomial by x minus 3, it yields a remainder of 52. Likewise, we have another equation, in which case we're going to say the polynomial evaluated at negative 2 is going to equal negative 18. And again, that's direct application of our remainder theorem. When you divide the polynomial by x plus 2, you get a remainder of negative 18. So the two equations this creates are 52 equals 27 plus 9a plus 15 plus b, and negative 18 equals negative 8 plus 4a minus 10 plus b. So let's simplify these two equations and see what we get here. Simplifying these two equations, we get 9a plus b equals 10, and 4a plus b equals 0. You can solve this using substitution or elimination. I'm going to go ahead and do elimination on this. Doing subtraction, we could eliminate the b's, in which case I get 5a equals 10, so my a value here is 2. Substitute this into either equation, I'm going to get, 4 times 2 plus b is 0, in which case I get my b value is negative 8. So therefore, the polynomial here that has these two characteristics must be x cubed plus 2x squared plus 5x minus 8. And that is the polynomial such that when divided by x minus 3 has a remainder of 52, and when divided by x plus 2 has a remainder of negative 18. Let's take a look at another example. In the next example here, they give us a polynomial and they say it's divisible by 2x plus 3. Find the value of k. So we know all the values, all the coefficients. We just do not know this coefficient here. We want to find that value. And the only piece of information they give us is 2x plus 3 is divisible, or in other words, 2x plus 3 is a factor. So if 2x plus 3 is a factor, that means that in this case here, we could rewrite this as you have 2x plus 3 is actually equal to 2, and you can have this as x plus 3 halves. So if 2x plus 3 is a factor, it also can say that x plus 3 halves is also a factor, in which case here we can use our remainder theorem. X plus 3 halves must divide this polynomial. Therefore, the polynomial, in this case here, p at x, at the a value, so in this case here, minus 3 halves, must equal 0. Right, so just to make sure that you caught that piece of information, they tell us that 2x plus 3 is a factor. If 2x plus 3 is a factor, then x plus 3 halves is also a factor. So therefore, x plus 3 halves divides this polynomial. So the polynomial at negative 3 halves must be 0, using our remainder theorem. So subbing this in here, we get 2 times negative 3 halves to the power of 3 plus 3 times negative 3 halves squared plus k times negative 3 halves plus 5 is 0. You can see here, simplifying a bit, I just expanded out, applied the cubic to the numerator and denominator, likewise the power of 2. And we end up getting this expression here. Simplifying a bit, we're left with this statement here, and you can see quite clearly these will cancel, and I'm now left with minus 3k over 2 plus 5 is 0. So I have to solve for k here. So going ahead and bringing the minus 5 to the right-hand side, multiplying across by 2, and dividing out, I get k equals negative 10 over negative 3, in which case we get 10 over 3. So this is one way you can go about solving this type of problem here using our remainder theorem. It's fairly direct application. Let me show you another way we could have approached this problem using synthetic division. So using synthetic division, if you remember, and again, if you aren't familiar with synthetic division or you need a refresher, I'll link that lesson in the top right-hand corner, but the idea is the coefficients of your polynomial. You write down, so we had 2x cubed plus 3x squared plus kx plus 5, and then the root of that divisor, in this case minus 3 halves, you put here. So how it works is we first drop the 2 down, and then through multiplication, we're going to take minus 3 halves times 2. Minus 3 halves times 2 is negative 3. The operation is always addition, so 3 plus negative 3 is 0. Multiplying, we get 0. Adding, once again, we get k. And multiplying this out here, we're going to take minus 3 halves times k will give us minus 3k over 2. And now again, through addition, we add these up. This is my remainder, and my remainder here is going to be 5 minus 3k over 2. So as discussed here, the factor 2x plus 3 is a divisor of our polynomial, so therefore this is a root of our polynomial, in which case I know that the remainder here must be 0. So we set this equal to 0, and you can probably already see what's going to go on here. We can multiply across by 2, and solving for k, once again, you'll get 10/3. So just another way to go about doing this using synthetic division. And again, synthetic division relates to, you need a linear divisor for this one. All right, let's take a look at the next example. For the final example here, they give us a polynomial of degree 3. Again, we want to find the k value, which is here. This time it's our constant term. And we know that when it's divided by 1 plus x squared, it has a remainder of 10. Find the value of k. Now notice here, we can't go ahead and do our remainder theorem results because the remainder theorem dealt with division by a linear factor, and we're actually dividing by a quadratic factor here. So going ahead and applying those results aren't possible. In addition, we can't do this using synthetic division, as synthetic division applies to linear factors as well. It's just a quick way of dividing polynomials when you're dividing by linear. So what we're going to do now is go ahead and do long division, still using the results of our division algorithm. In that case, I mean the polynomial, in this case p at x, breaks up into quotient times divisor plus remainder. Going ahead and using long division, we're going to have to put a 2x up here, giving us, subtracting, we get 7x squared plus k. Going to have to put a plus 7 up here, and subtracting, this gives us k minus 7. So now we know that this k minus 7 represents our remainder. Now 1 plus x squared is not a factor. It is not divisible by our polynomial p at x. However, it does have a remainder of 10. So therefore, it must be the case that k minus 7 must equal 10, in which case here we get k equals 17. So the polynomial, which when divided by 1 plus x squared yields a remainder of 10, is the polynomial 2x cubed plus 7x squared plus 2x plus 17. So that k value has to be 17. All right, that concludes our lesson on the remainder theorem. Please take a look at these examples here, and good luck.